welcome everybody. Oops, probably getting an echo. I need to mute this. There we go. That should improve that. Okay, so welcome everybody. Continuing our discussion. Are there any questions or concerns when we get started here? Anybody want to ask anything? Or I'm not getting too many emails from this class, so again, I sort of assume that people aren't having any issues. If you're having issues, please let me know. That way I can modify what we're doing to make sure everyone's getting taken care of. Okay, no issues. Then it looks like we are ready to move into systems of equations. Systems of equations is a hugely important area in mathematics. It gives rise to what's called linear algebra, which is one of the most widely used areas of mathematics. Not like in everyday life necessarily, but you know, any business out there, like business type situations, research, there's systems of equations that can be solved that can help optimize that system, help you solve problems that can be worked. I know some of the word problems we do in this class, you know, in an algebra class, some of the word problems seem silly, right? So that's one reason that I think people don't take those problems seriously. But being able to solve a system of equation is a hugely important tool to sort of help you be able to do things. So just understand, this is very important. Those of you who are going to be engineers or mathematicians or physicists, or I don't know if chemists have to take it or not, but if you're going into like a STEM field, you will definitely, once you come out the other end of calculus, you take this course called linear algebra. And it's basically just an entire course on basically systems of equations and matrices being used to solve systems of equations and a whole bunch of stuff related to it. Very, very important area of mathematics. Some of you don't need calculus and stuff, so you won't see them again, but they still can be very helpful. Even some basic problems can be solved with systems of equations, and without system of equations, you're just not going to get that thing solved, right? So let's try to make sense of what is a system of equations. Well, when we talk about a system, we just really mean a grouping, a collection of equations. Okay, so what we want is a collection of equations that we can satisfy all at the same time. So remember before, what we were doing is you would find a solution to one equation. Well, imagine if I gave you two equations and said, find a solution to both of these equations. There, that's a system of equations problem right there. That's all you're doing. So it's instead of finding a solution to one equation, you're finding a solution that fits two equations. That's what you're doing. Okay, so let's remind ourselves what an equation is just in one scenario, right? Because we're dealing with systems of linear equations. That is, they are lines. Those of you who end up in college algebra, pre-calc, trigonometry, stuff like that, you'll do systems of equations that are nonlinear. So you might have circles and then parabolas and ellipses and hyperbolas and, you know, different shapes ending up in polynomials ending up in your systems. But those are kind of a special case. The very widely used area in mathematics is usually systems of linear equations. And we're going to look at the basics of that in here. Those of you who are taking Math 3, intermediate algebra next semester, or whenever you take it, you'll do systems of equations again in that class. So if you learn it well here, then it'll be easy next semester when you basically do the same thing again. Now, I will say the problems that you do next semester will be a little bit harder, but they're not that much harder. If you understand the basics of systems of equations, that's sort of the difficult part. The other stuff is just, you know, algebra, just being a little bit clean with your algebra, make sure you're paying attention, and you can do those harder problems. So if you learn it here, it'll help you next semester. There's a few chapters like that. So let's just take one line, right? Y equals 2x minus 1. So there's a basic line. How's that showing up? Let's make this big. Okay, y equals 2x minus 1. So there's a line. Happens, you know, I happen to pick one that is in slope-intercept form. Well, what does this equation really have to do with this basically picture version of the graph over here? How are those related? Well, we think of this line, a lot of times we look at it and go, I don't know, it looks like a bar or some kind of a beam, right here. But it's not really like that. It's not really like one big solid thing. What it is an infinite number of points, right? Sort of all existing really, really close to each other. What are those points? Each one of those points represents a solution to this equation over here. For instance, let's take the example of the point 1, 1. 1, 1 is a point on this line. So that means x equals 1, y equals 1. If you plug in 1 for x and 1 for y, what do you get? You get 2 times 1, which is 2 minus 1. So 2 minus 1 equals 1. So 1, 1 is a solution. If I plug 1 in here for x and 1 in here for y, it works, right? Okay, well, what if we pick another one? What if we pick another point on here, 2, 3? Well, that's a point on the line, so it should work. So if I plug in 2 for x, I get 4 minus 1, which is 3. Yep, that's my y value, 3. That works. So all the points on this line, although we look at it and we start to see the shape, really, it's just an infinite number of solutions to this equation over here. So think about that. The points on the line are the solutions to the equation. Okay. Well, all right, then what if I give you a system of equations and say 2x plus 3y equals 6? That's not what I want. Here we go. This works. So now I have 2 lines, and I'm asking you to find the solution to the system. Remember, a solution to the system of equations means that the solution has to satisfy both equations. Because we can find an infinite number of solutions to satisfy the first equation. That's just any of the red dots. We can find an infinite number of solutions to satisfy the purple equation. That's just any of the purple dots. But how do I find a solution that satisfies both of those at the same time? Well, let's just use the logic that we worked through a moment ago. Any point on the red line is a solution to that equation. Any point on the purple line is a solution to that equation. So is there a point that is on both the red line and the purple line? Yeah, it's the intersection point, right? So the intersection point of these 2 equations is the solution to the system of equations. Because it's a point on the purple line and it's a point on the red line, well, then it must be solutions to both. So it looks like our solution is 3, 0. So let's plug that in. 3, 0. Okay, and let's just see if it works. So x is 3, y is 0. Let's see. If I put x is 3 here, I would get 6 minus 6 is 0. Yep, that works. All right, what if I put it down here? This would be 6 plus 0 equals 6. Yep, that works. See how it works in both of them? And what I just showed you, most of the time it's going to be more work to find the solution. But one great thing about systems of equations is it's way easier to check your work than it is to find the work. Okay, and you generally want to check your work with systems of equations because it's very easy in the systems of equations to make a mistake, right? You might look at this and go, how could you make a mistake? We're graphing it. But most of the time we're going to be doing these algebraically. And I don't know if we're going to get to algebraic methods today or not. We'll kind of see how fast we move through things. I just lost my train of thought. But anyways, so what we want to do is find those intersection points between the lines. Those are the solutions. And then you check them, right? That's what I was talking about, was checking them. You'll get an answer. Whether you make a mistake or not, you'll get a solution. But sometimes that solution is going to be wrong. So what you want to do is double check by just plugging your values in at the end. And then you know 100% you got it right. If it works, you're like, yeah, I totally got this correct. Because it works in both of them. Okay, and then you know you did the correct thing. Otherwise, I see it all the time where a student will make a slight negative mistake, right? They drop a negative, or they, here's a popular one that I see, which is it's just people being nervous during an exam, but they'll go, oh, 4 times 5 is 9. So they meant to multiply them, but what they accidentally did in their head was add them. I know that people don't think that 4 times 5 is 9, but it's just one of those things you do when you're nervous on a test and you're distracted. But you can catch that by checking your work at the end. Okay, so always a good idea to do that. I highly recommend. Oh, I forgot to have my water this morning. I'll be right back. I got to grab a water. Okay, thanks. So hopefully you're looking at this and going, that all seems really easy. If I want to solve a system of equations, all I have to do is throw it on a graph, find the point of intersection, and then that's it. Well, what's difficult about that? Well, there's a couple problems. One is we are starting off, when you learn systems of equations, you learn it with two variables in two equations, and that's what we're looking at. Next semester, you'll do three equations in three variables. Well, that becomes three-dimensional. So you can't just graph it on a 2D plot anymore. So that makes it a little harder. But here's actually the main reason, the main drawback. See how that, let's make it even more clear. Well, that's about the same. But notice how that point of intersection does not land perfectly on a grid line. So, like, even if I hover over this, it's going to give me an estimate of the in fact, in this one particular case, let's make it like this. Let's look like that. So, in this case, it's still giving us decimals that we could convert to fractions. But a lot of times what's going to happen is your solutions here come out so messy that you can't convert them to exact answers. Like Desmos will just be giving you approximations. Like, you know, sometimes when you look it up and it's like 0.66667 or something. That's not an exact answer. That's an approximation of the answer. And that happens a lot. So what happens is when your solutions don't happen nicely on these grid lines where they're perfect integers, like we got so far where it was like 2, 3 or 5, 1 or something like that where you have integer solutions, then the graphing method just starts to fall apart and it doesn't give you your answers. And in reality, most of the time, most of the real world systems of equations are probably going to include fractions, right, of some type. Not a ton of the ones we do in this class because you're just learning systems of equations. A lot of those will be integers, although there will be some with fractions. But in the real world, a lot of times it's fractions, right? We teach math where we sprinkle in fractions, but that's because you're learning. But, you know, just think of it. When you go to the store and buy something, how often does your price come out a perfect integer? Right? Not very often. Usually there's some cents and stuff. So there's, you know, decimals, fractions coming into play. You'd expect to get a perfect dollar amounts about 1% of the time, right? That's not very often, right? Just from a probability standpoint. So what's going to happen? What are we going to do about that then? If I just taught you graphically and then said, well, most of the time we don't use the graphical method, then why did I show it to you? And also then what are we going to do? Well, the graphical method is really, really good for students to be able to get a mental image of understanding how systems of equations work. If we just dove right into the algebra, students would just memorize how to do it and they wouldn't really have any kind of like conceptual understanding. So we look at the picture to help give us that contextual understanding of how the thing looks. Because there's going to be 3 different pictures that you want to keep in your head. There's going to be the picture of this. This is what's going to happen 90 to 95% of the time you do a problem. This is what it looks like. You're getting a system of equations. There's a single point of intersection, and that's how the game is played, right? I'm going to show you 2 other types of solutions that you can come up with, and they're a little harder to recognize in the algebra, so it's nice if you have the corresponding picture that can pop up in your head and go, oh, that's right, this is that kind of problem. Okay, so the graphical, even though in real life very, very rarely do people use graphical representations to represent, to actually solve systems of equations, it's really helpful in order to understand systems of equations, to be able to look at the picture of it. So, so that's part of it, right? We will then, I don't know if we'll get to it today or if we'll start next time with the algebraic versions of systems of equations. The algebraic versions are nice because they will get you your answers every single time, all right? And they both work every single time. We're going to have two major methods for solving systems of equations algebraically. One's called substitution. One goes by two different names. Some books call it addition. Some books call it elimination. It's the exact same thing. But the nice thing is if you use substitution or you use elimination, you'll get your answer every single time. Whereas the graphing method only gets you your answer sometimes. And you might go, okay, well, if there's two methods for solving algebraically and they both work every time, can't I just learn one of them? And the answer, unfortunately, is no. Because what happens is there's certain problems that are way, way easier with substitution. And there are certain problems that are way, way easier with elimination. So what you want to be able to do is know how to do both of them. And then go, oh, I'm going to use substitution on this problem because it's going to be like, I'll be done in like a minute. And that person next to me who's doing it the other way is going to take like 10 minutes to do it, right? So that's helpful. Plus, the tools that you use in substitution, you're going to use in other areas of mathematics. The tools that you learn in the elimination method, you're going to use in other areas of mathematics. So it's kind of helping you get used to some concepts, which you're going to see again and again. So you might as well be good with them. So like most of the time, when I'm teaching a topic in mathematics, if there's just like, there's usually multiple ways of doing something, I always like to just teach the one that I think is the best. But with systems of equations, you really need to know both ways to work on those systems of equations, okay? Like I say, we'll get to those algebraic methods maybe later today, maybe next time. But first I want to show you those other things that can occur when we have a systems of equations. So remember, this is what you expect to see most of the time. You have two lines, they cross at an intersection point. That intersection point represents your solution. You double check your work, you're done, you move on to the next problem. But if you played around with this a little bit, you'd see, well, maybe there's an issue. What if I had, I've got these equations in slope-intercept form. What if I had two equations that were parallel? Oh, we don't want them both red, though. Look, two parallel lines. So where is the point of intersection of these two lines? Well, they're parallel. There's never going to be an intersection. It's like train tracks, right? You ever stand on a train tracks that like just go off straight forever to the horizon? They just never intersect, right? These two, I mean, they might look like they do as you get near the horizon, but you know that the two railroad tracks, they don't come together at a point. They're always side by side with a gap in between them. That's what we have right here, right? There is no point of intersection to these two lines. Well, but a minute ago I said that the solution to a system of equations was the point of intersection. Well, so what does that imply? If these two lines have no point of intersection, then they must have no solution, right? There must be no solution to the system of equations. That's right. There is no solution to the system of equations. So it is possible for you to have a system of equations in which no solution exists. So we did the first example that we looked at a minute ago, and we had one solution to that system of equations. We now have an example of a system of equations that has no solutions. So far we've seen 0 solutions and 1 solution. There's one more possibility. Let me see if I can do this well. So let's see. Now, when you just look at these two lines, just look at the algebra over there. Y equals 2x minus 3 and 6 plus 2y equals 4x. if I just handed you that system of equation, you're probably not going to immediately go, wait a minute, those are both the same equation, right? You're probably not going to recognize that right away. Some of you might, but most of us are not going to recognize and go, wait a minute, is that the same equation but written differently? But sure enough, we can see, look, these are the same equation. See how when I turn on that blue line, it's right on top of the red one? Because this is actually two ways of writing the same equation. So what did I do? You go, wait, how could they be the same? All I did was take this top equation and double it. So 2y equals 4x minus 6, and then I moved the minus 6 over to the left. So it's literally the exact same equation. Well, what does our logic tell us then about this particular problem? If the solution to a system of equations is the point of intersection, and these two lines are right on top of each other, how many points of intersection do they have? Infinitely many, right? They have an infinite number of points of intersection, meaning there's an infinite number of solutions. Now, back like 10, 15 years ago, math textbooks used to expect that as the answer, where they would say, what is the solution? And then you'd write infinitely many solutions. But it's actually not a very good way of answering the question, because that's not how we answered the first question, right? When we solved for that one point of intersection, we didn't say, okay, everybody, it's good. We figured out there's one solution. No, you want to know what the solution is. You want to be able to represent what the solution is. So we answer those questions a little differently than we did before. So they work the same way, but we're sort of giving a better answer than we used to ask before. But those are the three pictures that you should have in your mind. When the two lines are actually right on top of each other, that's one. And then the example where we had, like a moment ago, two parallel lines where there's no intersection. And then the one where, this is what you get most of the time, where there's one point of intersection. You should be able to have those three in your brain, because you're going to want to think, which one am I working on from the information I'm getting in the problem? Which of these am I doing, right? The one where they cross and you have one point of intersection, the one where they're parallel and you have zero intersections, the one where they're the same line and you get infinite solutions. All right, which is the one you're talking about? So when we get into the algebraic methods, we're going to have to figure out, what do these three scenarios look like when you're doing the algebra? Like, how do you recognize, if you never graph these, how do you recognize which of the three it is? And we will do that, not today. We're definitely not going to get to that. So we'll do that in the future, okay? So let's take a look at a couple of these delta math problems, okay? Solve linear systems graphically level 1. Let's take a look at one of those. So guess what? They're giving you some lines here. You're going to have to graph the lines. So remember, we learned how to graph lines earlier. One of the most important topics you're going to leave this class with is how to graph lines. Even if you're just taking, and I shouldn't say just, like statistics is a totally legitimate course. It's not as strenuous or challenging as, say, a calculus course. But if you're going into statistics, you have to know how to graph lines, because you'll be doing it when you do your linear regressions, your line of best fit, your least squares lines. You have to graph those lines, and you have to interpret what they mean. So I would argue that one of your most important algebraic skills, I would argue the most important algebraic skill going into statistics is being able to graph a line, being able to interpret the slope, being able to interpret the y-intercept. Okay, so at least half of you will probably end up in statistics, probably more. So you're still going to have to remember how to do that. So solve the following systems of equations graphically on the set of axes below. Okay, so let's see how we can do this. Luckily, they're in slope-intercept form, so these should be pretty straightforward to graph. So y equals negative x plus 1. So that's what? That's a slope of negative 1 and an intercept of 1. So we've got a y-intercept right here at 1. And then we're going to go what? For negative 1, we're going to go down 1 and over 1, like that. So there's a line right there. Oops. Can't quite see it. So there's our line, right? I just used our slope-intercept interpretation. The intercept is 0, 1. I use the slope, down 1 over 1 to get the point. There's our line. Okay, now I'm going to do the same thing for the other graph. All right, so if I plug in 0 for x, I get y equals 6. So my intercept is 0, 6. And my slope says what? I'm going to go up 1 over 4. So I go up 1 over 1, 2, 3, 4. Put that dot there. And now I'm looking for the point of intersection. So let's see. My point of intersection appears to be -4, 5. -4, 5. Now, they want a certain way of submitting the answer on Delta Math. So just kind of pay attention to how that looks, and then you can put it in there the right way. When I'm using like paper and pencil tests in the classroom, there's two ways I accept the answer. One is you can say x equals -4, y equals 5. Or you can use the graphical representation where it's a point, and you can say it's the point -4, 5. Because both of those mean the same thing mathematically. All right, so you should understand that. But here they want it done a certain way. So they probably want it, let's see, do they tell us? Oh, this is, no, it doesn't say. So I'm going to put it in as a point and see if they like that. I'm going to put it in as negative because I can't remember off the top of my head. Let's do it this way. Submit answer. Yep, they liked it. They liked it written as a point, right? And they even do it. Solution to the system, written as a point. Okay? They've got the two lines, point of intersection. That's how that goes. All right, let's look at the next one. Next problem. All right, basically the same thing. So let's go back and try solving linear systems graphically level 2. Okay, solve the system of equations graphically on the set of axes below. Y equals 3x minus 8. X plus 4y equals 20. Okay, so the first one's going to be easy because it's in slope-intercept form. So I go down to -8. Got a point there. And then my slope is 3, so I'm going to go up 3. 1, 2, 3 over 1. There's my line. All right, this one's not in slope-intercept form. So how am I going to graph that one? Well, we could think about it in terms of intercepts, right? Put in 0 for x, and what does that make y? 5, right? What do you multiply 4 by to get 20? If this is a 0, multiply by 5 to get 20, so that's going to be 0, 5. All right, what if my y is 20? Then x needs to be 20. Oh, that's not going to work because our graph doesn't go that far. So a couple things you could do here. Let's do it this way. That shouldn't still be there, should it? Oh, yeah, it's down here. X plus 4y equals 20. Okay. Couple things we can do. X plus 4y equals 20. Okay, so I'm just going to show you again what I did a moment ago. As I said, okay, well then what happens when x equals 0? I'm just kind of reminding you how this stuff works. When x equals 0, where's my page? There we go. When x equals 0, in fact, we don't need that to be. That's going to be too big. Let's get rid of that. When x equals 0, we get 0 plus 4y equals 20. And then it's pretty easy from there to see that y equals 5, right? So that's what I just did a moment ago where we got this point right here. But now we have to figure out the other point. I'll show you why it doesn't work as well. Because if I say, okay, well, what about when y equals 0? Then we get x plus 0 equals 20, which is totally legitimate as far, like we found a point on here. Whoops. X plus 0 equals 20 because it's, wait a minute. when y is 0. Yeah, right. When y is 0, so that x equals 20. Sometimes if I don't write it out, people get kind of left behind, so I want to make sure. But look, there is no 20 on this axis. I can't go out far enough. So that point's not really going to work. So you have two choices. You could choose a different value and try to find another point, or you can put it in slope-intercept form. It's your choice, right? Since we have all these different tools for dealing with linear equations, the choice is yours. How do you want to do it? So let's see. For me, I'm thinking... All right, I'm just going to choose a value. I'm going to choose when y equals 4. Okay, so that means we have x plus 4 times 4 equals 20. So that really is going to give us what? X. So 4 times 4 is 16. Subtract 16 from both sides, you get x equals 4. So let me double check that works. 4, 4. Let me see. 4 plus, yeah, 4, 4 works. So I'm going to go over to the point 4, 4. In fact, it looks like 4, 4 is our solution. It just happened to be the point that I found for the one equation. Just happened to also be the point of intersection. So it looks like 4, 4 is our solution. And there we go. Okay. So here they chose to put it in slope-intercept form. That's not what I did. I plotted points, mainly because I'm trying to get you to remember this. I know you haven't looked at it for a few weeks, but I'm showing you so you go, oh, that's right, I remember doing that. And then you'll have these different tools, because the more tools you have to attack lines, you're just going to get better and better at it and understand it better. So that's how that part works, okay? All right, what's the next one look like? Nah, we don't need to do that one. Okay, now write systems of equations from context. I can imagine this will be some people's least favorite part, but let's work on it. Right, we need to, it's the same skill that we keep seeing in these different sections. You have to define your variables, and you have to use them appropriately. So this, again, there is no, like, magic rule that I can teach you that says anytime you see this statement, then it means this, right? Sometimes your pre-algebra books have actually tried to do that, and I think it doesn't help. Because it teaches people they can just memorize certain words and phrases when you can't. The reason that word problems are hard is because it takes critical thinking. There is no shortcut that you can just memorize that makes it work. You have to critically think your way through. You have to use reason and logic to make sense of it. And that includes reading the paragraph and reading it multiple times. Sometimes people just, they don't understand that reading math is different than reading, say, a novel or a history book or something. You know, if you're reading about the Roman Empire, you can just kind of read through it like a story and go, okay, I get it. Math textbooks and math, you can't read that way. Your brain starts to get kind of scrambled. You have to slow down. You might have to read one sentence or a phrase of a sentence 3-4 times to make sense of it and go, oh, now I get it. Right? And then you work your way through it. So this paragraph might take you 2 minutes of reading it to fully understand what's going on, whereas we probably could read that sentence in about 20 seconds, right? But if I just read through it really fast, we're not going to understand any of what it means. One thing that I stress when I'm trying to get my students to do systems of equations, and I watch them in the classroom skip the exact steps that I'm trying to get them to do, is they skip this. The part where they write what their variables represent, they try to skip that. And then they'll call me over and say, I don't know how to write my equations. And I say, well, what do your variables represent? And they go, I don't know. Well, yeah, how are you going to write equations if you don't even know what the variables are representing, right? It's like standing at an empty lot trying to build a house, and then someone says, well, what are you going to build with? And you go, I don't know. I don't know if I'm going to use wood or brick or what. Who knows? But I don't know how to do it. It's like, yeah, you have to do the prep work before you can do the actual work. But a lot of times in these math classes, students want to skip the preparation work and just get right to the thing that's going to give them points. Well, you can't do that. You can't skip the earlier steps, right? You have to know what your variables are in order to write equations that use those same variables. It just makes sense. Ask yourself the question, how could I write an equation if I don't know what the variables in the equation represent? It doesn't work. Okay, so let's try to make sense of this. A school is organizing a cookout where hot dogs will be served. Okay, so I just kind of stop there and catch my breath. Okay, so hot dogs are going to get served. All right, it's kind of gross, but okay. They're cheap, right? It's a cheap way to feed a bunch of people, a bunch of hot dogs. Okay, the hot dogs come in small packs and large packs. Okay, so we can buy different types of packs, and whatever our organization is probably trying to keep it cheap, so we got to figure out what makes the most sense. Okay. Each small pack has 10 hot dogs, and each large pack has 18 hot dogs. Okay, so I can either buy packs of 10 or packs of 18, or some combination. In reality, we're probably buying a combination of them. Okay. The school bought 6 packs of hot dogs that have a total of 76 hot dogs. Okay, so 6 packs, total number of hot dogs is 76. Okay. Write a system of equations that can be used to determine the number of small packs purchased and the number of large packs purchased. Define the variables that you use to write the system. Now, here's the example I talk about. This is a perfect example of kind of a stupid problem, right? Is anyone ever going to go back and try to determine the size of packages of hot dogs that were purchased by an organization? No, of course not. But if we gave you a real-world problem right out of the gate for systems of equations, it would be so complicated that you'd go, I'm lost. I have no idea what to do. So just kind of keep that in mind, because this is one of the reasons people hate these word problems. They're like, well, they're stupid, and why would I ever want to determine hot dogs? This kind of stuff is important in the real world. It's just you're not ready for an actual business problem, right? I mean, if a company is getting audited for its spending practices, and you can see in the budget, oh, well, we spent this much on baseball games to take our salesmen were taking clients to baseball games to try to close the deal on the sale, and we might want to know, well, how many of those tickets were box tickets and how many of them were regular seat tickets, right? If there's an audit going on, because this happens all the time where, a company wants to know, they come in and they go, maybe our business practices have been a little bit sketchy lately, the way we're spending money. Or sometimes what happens is someone is embezzling money. That is, they're sneaking money out of the company to try to keep for themselves, which, by the way, is never a good idea. You end up with a small amount of money, and then you end up going to prison. It's not worth it. But anyways, those are the kind of things that you actually would use you could use this kind of stuff for. No one ever uses this to figure out hot dog packages. I get it. But just do be aware, there are very reasonable situations where you could apply this to. We're just trying to keep it simple. Okay. So we need to define our variables. So you can determine your variables. A lot of times we choose X and Y. You're welcome to use X and Y, but why don't we be a little bit more clever? Why don't we pick smart variables? Let's be smart about this. Let's choose a variable which is going to keep us from getting confused, because one of the things that happens with systems of equations is that students will choose X and Y always for their variables. Well, if X stands for the number of small hot dog packages and Y represents the number of large hot dog packages, how likely do you think it is that a student will confuse those at the end and mix up the two variables? Pretty reasonable. I see it on tests all the time where a person's work is totally correct, and then they go back, their numbers are even right, but they've accidentally switched them, and they answered the thing incorrectly. So you get the right numbers, but you've switched them so that the number of large hot dogs you're writing as the number of small hot dogs, and the number of small you're making as the large package. And then sometimes students will protest and say, oh, but I did my work right, I just gave the wrong answer. Well, if you're at a business and the business loses a bunch of money because you switch your two answers, do you think your boss is going to care that most of your work was right? You only made the mistake in switching the two? They're not going to care. They're going to go, you cost us $100,000, you're fired, right? So a better approach is to choose smart variables. Why don't we choose S and L for small and large? If I'm clever and I'm smart here about the variables that I'm picking, is it likely that I'm going to mix up the S and the L? Am I going to get to the very end and think that the number of small packages is represented by L and the number of large packages is represented by S? Probably not, right? Probably, since we've used S and L, we can remember one of those is for small and one of those is for large, and we can go from there. All right, so what are our choices here for small? Well, the number of small packs purchased, number of large packs purchased, total number of hot dogs, hot dog packs, total number of hot dogs, number of hot dogs per small pack. Well, that was given in the problem. Why would we solve for something that's already given to us? And here, the number of hot dogs per large pack. That was given in the problem. Why would we solve for something we already know? We won't. Okay, so let's remind ourselves. Write a system of equations that could be used to determine the number of small packs purchased and the number of large packs purchased. Now, it's not always the case that your variable representation will be laid out right in the problem, but frequently it is. So let's have S be the number of small packs purchased and L be the number of large packs purchased. Okay. So now we've got our variables defined, right? And now we're not skipping ahead. This is that people like to skip that step, and again, they're trying to build a house without knowing which materials they're going to use. It doesn't make any sense. Now that we know what our variables represent, we can construct equations from those variables. All right, so there's oftentimes an equation that's a little easier to figure out and one that's a little harder to figure out. So let's see. The school bought 6 packs of hot dogs that have a total of 76 hot dogs. Boom, right there. That one sentence that seems like a pretty straightforward sentence, we're getting our 2 equations from that one sentence. The school bought 6 packs. Every pack that was purchased was either a small pack or a large pack, right? So then it stands to reason that S plus L equals 6. The number of small packs plus the number of large packs is equal to the total number of packs, which they're telling us is 6. Okay, cool. All right, let's see. Now, what's our other one? This one's a little bit trickier. There's a total of 76 hot dogs. So let's try to count hot dogs. So we know it's going to equal 76. But what's going to equal 76? Well, how many small packs do we have? We have S. And how many packs are there in each small pack? 10. So 10S is the number of hot dogs that came from the small packages. Okay, what do we need to add to that? The number of hot dogs that came from the large packages. Those have 18. So L is the number of large packages, and there is 18 of them, 18 hot dogs per package. So 10S plus 18L equals 76. The number of small hot dogs from the small packages plus the number of hot dogs from the large packages. Add all those together, you get 76. Let's submit our answer. There we go. Okay. So this is really good. It's a good way of sitting down and forcing your brain to set up these systems of equations, and you have to define those variables, which again is a step I see students really like to skip that step, and then they don't understand why they can't construct their equations. You got to define the variables first. Okay. Come on, time. Excuse me. Okay, so here's a problem where they just want you to come up with some different combinations. So determine 3 ways to have a total of 16 coins. Right? Aria has 90 cents worth of nickels and dimes. She has a total of 16 nickels and dimes altogether. By following the steps below, determine the number of nickels X and the number of dimes Y that Aria has. So you're just going to play around with this, and it's giving you your total value. So you're going to play around with these numbers till you get something that works. So this is kind of like a brute force method. You're sort of brute forcing the method to try to find the right combination. That's usually not how we want to solve systems of equations, but the point of this here is to get you to understand what we're doing when we solve a system of equations. That's the point of that problem. So play around with that one. Oh, that's the same problem I just did. And then here's the graphic one. So basically, they're kind of putting all those skills together. You're going to read this. You're going to define your variables. You're going to figure out what your equations are. You're going to graph them. And then the point of intersection is your conclusion. So it's just putting all those pieces that we just looked at, putting them all together, and going from there. Okay? So that's actually a good place to start because I don't want to get into the algebraic stuff today, and we only have 3 minutes left anyways. So I'm going to close the YouTube stream. Anyone who wants to talk to me in Zoom, please come do so, and I'm happy to have a conversation with you or answer your questions or help you in whatever way you need to make sure you're doing well in the classroom. Otherwise, I will see you in a couple days. All right, thanks, everybody.